Why maximizing resource utilization reduces performance? Many organizations believe that every machine, employee, and department should remain busy at all times. Idle time is treated as waste. Managers monitor utilization rates. Supervisors push teams to keep producing. Departments are rewarded for maximizing local output. At first, this seems logical. If a resource is expensive, the organization wants to use as much of its capacity as possible. But a system in which every resource is fully utilized often becomes slower, less flexible, and more expensive. Work begins to accumulate. Queues become longer. Lead times increase. Priorities change constantly. Small disruptions spread across the entire operation. This is one of the most dangerous misunderstandings in operational management. In this video, we will examine why high utilization can reduce flow, how local efficiency damages system performance, and how Lean Six Sigma helps organizations balance capacity, demand, and operational stability. This is the 6th episode of Modern Lean Six Sigma: Hidden Failures in Operational Excellence. The utilization trap begins with a simple belief. An idle resource is a wasted resource. This belief encourages managers to keep every employee and machine constantly active. If one department has available capacity, more work is released. If a machine is waiting, another batch is scheduled. If an employee finishes early, additional tasks are assigned. The organization appears productive because everyone is busy. But activity is not the same as flow. A department can produce large volumes of work while the customer waits longer. A machine can operate continuously while inventory accumulates between process steps. An employee can complete many tasks while the most important order remains delayed. The problem is that organizations often measure each resource independently. They ask, how much did this machine produce? How many tasks did this employee complete? How many hours was this department active? But customers experience the performance of the entire process. They care about quality, lead time, reliability, and value. A resource can be locally efficient while the overall system becomes worse. When a resource operates close to 100% utilization, even a small disruption can create a large delay. Demand is rarely perfectly stable. Processing times vary. Employees need support. Machines experience minor stops. Information arrives late. Priorities change. Rework enters the system. If there is no available capacity, the process cannot absorb these normal variations. Work begins to wait. Imagine a machine with capacity for 100 units per hour. If demand remains exactly at 100 units every hour, the machine has no room for any interruption. A short setup delay, quality check, material problem, or equipment stop immediately creates a queue. The next hour begins with unfinished work. The machine must now process current demand and recover the previous delay. If the same condition happens again, the queue continues to grow. The resource remains busy. Utilization looks excellent, but lead time becomes worse. This is why a process can appear highly efficient while customers experience increasing delays. As utilization increases, waiting time does not increase in a simple straight line. At lower utilization, the process may absorb normal variation without major difficulty. But as the resource approaches full capacity, waiting time can rise very quickly. A small increase in demand may create a much larger increase in queues. This effect is common in production, healthcare, customer service, logistics, software development, and administrative processes. A hospital may schedule every specialist with no available space. A call center may staff exactly for average demand. A warehouse may operate every loading dock at maximum capacity. A project team may assign every employee to 100% of their available hours. Everything works while conditions remain perfect. But conditions rarely remain perfect. One urgent case arrives. One employee is absent. One machine stops. One project requires rework. One customer changes the requirement. Without protective capacity, the system becomes unstable. The organization then reacts with overtime, expediting, rescheduling, and constant priority changes. These actions increase cost and complexity. The problem is not that people are working too little. The problem is that the system has no room to respond. The utilization trap also affects knowledge work. Managers often believe that assigning every available hour increases productivity. Employees participate in multiple projects. Their calendars are completely full. Tasks are divided across teams. Everyone appears busy, but work does not move smoothly. An employee begins one task, receives an urgent request, switches to another project, joins a meeting, responds to emails, and then returns to the original activity. Every interruption creates a cost. The person must remember the context. Files must be reopened. Information must be reviewed again. Attention must be rebuilt. This is the cost of task switching. When employees are assigned to too many activities, they may complete fewer tasks even while working harder. Work in progress increases. Completion time becomes unpredictable. Projects wait for small contributions from overloaded specialists. The organization measures effort, but the customer experiences delay. A team with slightly lower utilization may complete more work because it can focus, finish, and respond to problems faster. Lean management distinguishes local optimization from system optimization. Local optimization improves one resource, department, or metric. System optimization improves the entire value stream. Suppose a cutting machine can produce material faster than the next process can consume it. To maximize utilization, the company keeps the cutting machine running. Output increases. The department reports excellent productivity, but material accumulates before the next process. Inventory rises. More space is required. Material handling increases. Defects may remain hidden inside the queue. Priority orders become difficult to identify. The cutting department is efficient. The value stream is not. The same thing happens in offices. A sales team may generate more orders than engineering can evaluate. Engineering may release more projects than operations can execute. Purchasing may buy large quantities to reduce unit price. Each department improves its own metric. The organization creates more work than the system can complete. Operational excellence requires flow, not maximum activity, at every point. In most processes, one resource limits the total output of the system. This is the bottleneck or constraint. Producing more before the bottleneck does not increase final throughput. It only increases inventory and waiting. Producing more after the bottleneck may be impossible because the required work has not arrived. This means not every resource should operate at maximum capacity. Non-bottleneck resources should support the pace of the constraint and the needs of the value stream. Imagine 3 process steps. The first can produce 100 units per hour. The second can produce 70 units. The third can produce 90 units. The system cannot sustainably produce more than 70 units per hour. If the first step produces 100, 30 units begin to accumulate before the second step every hour. The first resource is highly utilized, but the system is not producing more finished output. The organization is only creating work in progress. The correct objective is not to maximize every resource. It is to protect and improve the flow through the constraint. Organizations often continue producing because their performance indicators reward activity. Machine utilization, labor efficiency, departmental productivity, units produced, cost per unit. These metrics may encourage teams to create output even when the next process does not need it. Large batches can also make local performance look better. Setup time is distributed across more units. The cost per unit appears lower. But large batches increase inventory, waiting, and response time. They make problems harder to detect. They reduce flexibility when customer demand changes. Another reason is psychological. Visible activity feels safe. A running machine looks productive. A busy employee looks committed. A full schedule looks efficient. Available capacity may appear uncomfortable because it raises questions. Why is this resource waiting? Why is this employee not assigned to another task? But some available capacity is not waste. It may be the capacity required to absorb variation, solve problems, perform maintenance, improve the process, and respond to customers. The question is not whether a resource is always busy. The question is whether the system is producing reliable value. Protective capacity is the available capacity used to protect the flow of the system. It allows the operation to recover from variation. It supports urgent demand. It provides time for training, maintenance, problem-solving, and continuous improvement. Without protective capacity, every disruption becomes a crisis. Consider preventive maintenance. If a machine schedule is always full, maintenance may be postponed because there is no available time. The machine continues operating until a failure occurs. The organization avoided planned downtime, but created unplanned downtime. The final loss may be much greater. The same applies to employees. If every hour is committed to immediate production, there is no time to improve standards, analyze defects, develop skills, or remove root causes. The organization becomes trapped in daily execution. It remains busy but does not become better. Protective capacity should be deliberate. It does not mean accepting uncontrolled idle time. It means designing enough flexibility for the process to remain stable. To escape the utilization trap, organizations need better measures. Utilization can still be useful, especially for constraints and expensive resources. But it should not be used alone. Leaders should also monitor lead time, throughput, work in progress, queue length, on-time delivery, first pass yield, flow efficiency, customer response time. These indicators reveal how well work moves through the system. For example, an employee may be utilized 98% of the time. But if tasks remain open for several weeks, the high utilization is not creating fast flow. A machine may run continuously. But if finished goods inventory increases, production may not be aligned with demand. A department may complete many activities. But if downstream teams are overloaded, local productivity may be damaging overall performance. The best metric depends on the objective. But the organization should never confuse maximum activity with maximum value. Lean Six Sigma helps organizations understand where capacity is needed and where work is accumulating. Value stream mapping reveals processing time, waiting time, inventory, and handoffs across the complete process. Process mapping helps identify where queues and delays are created. Little's Law connects work in progress, throughput, and lead time. Reducing work in progress can shorten lead time and improve visibility. Takt time helps align the pace of production with customer demand. Constraint analysis identifies the resource that limits total system output. Standard work reduces unnecessary variation in processing time. Setup reduction increases flexibility and makes smaller batches more practical. Statistical analysis helps teams understand demand patterns, process capability, and sources of variation. The objective is not simply to reduce capacity. It is to use capacity where it creates the greatest benefit for the system. The first step is to identify where work waits. Look for growing queues, delayed approvals, excessive inventory, overloaded specialists, and recurring expediting. Next, compare demand with real capacity. Do not use only average values. Consider variation, downtime, rework, absenteeism, setups, and changing priorities. Then identify the constraint. Which resource truly limits the output of the system? Protect that resource from avoidable interruptions. Ensure that it receives complete information, correct materials, and properly prepared work. Control the release of new work. Do not introduce more work into the process than the system can complete. Limit work in progress. Create clear priorities. Reduce multitasking. Use smaller batches when possible. Finally, create protective capacity in critical parts of the process. The goal is not to make people work less. The goal is to make workflow better. High utilization can look impressive. Machines are running. Employees are busy. Schedules are full. Departments report strong productivity. But underneath that activity, queues may be growing, lead times may be increasing, and customers may be waiting. A system with no available capacity has no ability to absorb variation. Every interruption becomes a delay. Every urgent request creates disruption. Every problem requires expediting. Modern Lean Six Sigma requires a different perspective. Do not optimize every resource independently. Optimize the flow of value through the entire system. Protect the bottleneck. Control work in progress. Reduce multitasking. Measure throughput and lead time. Create enough flexibility to respond to normal variation. And remember, a busy resource is not necessarily a productive system. The objective is not to keep everything moving. The objective is to move the right work at the right pace through the entire process. Because operational excellence is not defined by how busy the organization appears. It is defined by how reliably the system delivers value. In the next episode, we will examine why continuous improvement fails when employees do not feel psychologically safe enough to report problems and challenge existing practices. Subscribe to the channel and continue exploring the hidden failures in operational excellence.